Well, thank you so much for having me. I'm very excited to come and talk to you about this new NASA grant that we just was awarded over the summer. And what we're doing for that is we are designing and developing an entirely new type of aircraft wing that we're hoping will reduce fuel needs by 70%. So we're hoping to make a very transformative impact on commercial air flight. And I'll tell you all about it today, and we'll do a little bit of Aircraft 101 on why it's going to work, so you'll be able to talk engineering with your friends on how aircraft work at the end. So in general, what I'm going to talk about today is I'll give you an overview of this NASA program that we won, and then talk to you briefly about what our UT team is doing here. And then, like I said, we'll do some Aircraft 101 on how the aircraft works and how the wing is going to revolutionize the fuel efficiency. And then another big component of this is education. Obviously, we want to educate our next generation of engineers, and we have a very substantial education program as part of this grant, impacting kindergarten all the way through graduate students. So we're really excited to implement the education plan too. Okay, so first of all, a little bit about NASA. Obviously, we all know what NASA is. The particular branch we're working for is the Aeronautics Research Mission Directorate. What they do is they're primarily focused on research that is going to transform flight, particularly through fuel efficiency and safety. So they're the group that awarded this. They have a very long history of advancements in aviation for decades. In particular, the group I work with the most is NASA Langley, and they're celebrating their 100th anniversary this year. So NASA has a very long history of supporting research and transforming aviation. And pretty much every commercial aircraft in our control towers have some sort of NASA-developed or NASA-funded technology. So they're continuing to work and fund projects that will continue to advance safety and fuel efficiency and keep us traveling. Okay. The three main focuses of the NASA ARMD are global, sustainable, and transformative. So one of the reasons our project was picked is we're going to show how we hit all of those. We're putting it on commercial aircraft that can either travel within the United States or worldwide. Sustainable, we're hoping to really improve fuel efficiency for a more sustainable future. And this new wing, if we can achieve what we think we're going to be able to do, will be transformative. So of the 6 thrusts that the ARMD focus on, we're going to talk today about this ultra-efficient commercial aircraft vehicles. But they do support, 6 different thrusts to achieve their mission. All right, so as far as the transformative and the new sustainable, why does our wing fit these criteria? Well, if you look at 100 passenger aircraft is what our new wing is going to go on. We're hoping to satisfy the N+2 and N+3 fuel efficiency goals. Now, what's N+2 and N+3? N means what's the state of the art right now. So what's the current aircraft? And then +2 would be 2 times 5. So N+2 would be in 10 years from a current aircraft, and N+3 would be 15 years in the future. So we're hoping to meet our goals for 15 years from now with this new wing for fuel efficiency. So by focusing on this type of aircraft, if we look at 100 to 200 passenger planes, typically as they are now, so that's your single aisle. You're going to learn what transonic means soon. Just the fuselage and the wing type of planes, that's about half of our total fuel consumption for our fleet of planes. Okay? If we then add even the bigger planes, they're the same type of configuration, but higher passengers, we're at 85% of the current fuel efficiency. So if we can put a new wing on that's going to make these planes 70% fuel efficient, that would be a huge impact on fuel consumption for our country and for the world, to tie into the global. So this is our goals that we're hoping to achieve and how we fit into this NASA ARMD mission. Now, the particular funding mechanism that NASA uses to fund these types of projects is called the University Leadership Initiative. So the goal of that is to have university-led projects and university leadership to help meet their missions. So NASA funds university teams to go and tie in. And the really great thing about this was we were allowed to write any grant on any topic as long as it fit within their mission. So we were able to pick, particularly what we wanted to do. And again, these ideas for the University Leadership Initiative are supposed to be really innovative and transformative. We want to revolutionize aviation. It was a very highly competitive award. They only funded 5 teams this year, and we were one of them. So you can see we had, we're part of a very elite group of universities. And you can see every single one of these topics is going to somehow transform aviation, whether it be through new wireless communication networks and data sources to help us have better air traffic control, trying to minimize sonic boom, Texas A&M, looking at different types of propulsion. And then ours is focusing on the aerodynamics of the wings. So these were the 5 winners for this year. Specific details about the UT award, you were told it's a $9.9 million effort for 5 years. We're part of Thrust 3 with the ultra-efficient commercial air vehicles, and we're hoping to demonstrate 70% fuel efficiency through a new type of wing, which I'll tell you all about in a few minutes here. One thing I want to emphasize is that this is a very multidisciplinary effort. We have a lot of teammates nationally, and it's going to take a lot of different people from a lot of different disciplines to come together to do this. It's not just one field. There's a lot of different professionals that are going to work together and merge all of our very distinct research components into this new wing. And of course, education is just so important. We're going to tie all of our research in. We're going to have a lot of hands-on work by the students and get out and do a lot of outreach on K-12 to try to get more of our young people excited about coming into engineering. As you can see, our research team is nationwide. We have outstanding partners from Penn State all the way right coast to coast. We do have 2 professional partners, in particular Boeing. The general shape of the wing, as we're going to talk about, is a Boeing design. So they're on our team to help us with the overall shape of the wing. And then the airfoils company did the very specific cross section. So they're providing the baseline that we're going to take and make a step better and optimize. And then all of our university teammates each have a particular expertise that they're going to lend to the project. As you can see, I want to put this slide up to really show how many people are involved in the multidisciplinary. So this is our new design center that University of Tennessee is leading under Dr. Jim Coder. He's another assistant professor in my department, and he's the principal investigator and was just the greatest leader in helping us to get this. And then I'm in charge of the educational component and the structures. So I'm going to be the one that once they're going to design the overall shape and the aerodynamics and the loads, and then I'm going to make sure that it holds the loads and doesn't break and do all the internal structure of the wing. But you can see we have many, many people across the country that are going to be involved in this wing. And also importantly, we're putting together a panel of subject matter experts that are going to meet with us regularly to provide input. So that way we can take nationally all the expertise that we have in the country to help us put this wing together. All right, so let's talk a little bit about the wing itself and how it works, just to give you some aircraft design 101. So if you have an aircraft, for example, the Joint Strike Fighter, okay, what we need to worry about the wings are 2 primary things. One is the lift, okay, so the lift is what's going to keep the plane up in the air. And obviously, gravity is trying to pull it down. Okay, so we need to generate enough lift to keep it going. And then your thrust is what's going to move it forward, and that's going to be resisted by what's called drag. Okay, interestingly enough, everybody tends to think about having the engines and the thrust as part of the lift. It's not. If you think about like a hang glide or a kite, right? They don't have engines, but they can still fly. Okay? So your lift is going to be concerned with the area of the plane in this direction. So how much lift I have I'm going to show you it's proportional to the area in this direction. All right? How much drag is trying to stop the engines is going to be your cross-sectional area looking at the plane. So how much area in this direction is being resisted by the air going forward. Okay? So for our wing, we want to have lift to keep it up in the air, so that's going to be this top area, and we want to minimize drag because the more drag we have, the more fuel and the harder the plane has to work to go forward. Right. Oh, and I should also point out, most of these slides, NASA has a great resource for education. So a lot of these slides I took from the NASA. So if anybody wants to learn more, it's Glenn Research Center. And they have some great just topics. You can hit on just pretty much anything you want to learn more about aircraft. So For those of you more mathematical, I give you the equation, or you could also look at just the plain English. All right, so the first thing we want to think about is lift. Okay, so there's a particular coefficient based on many different pieces. There's the density of the air, okay, velocity squared for how fast it's going, and then, like I said, this wing area, and that's going to tell you how much lift you have. So we want to maximize lift. Okay, drag, you have a different drag coefficient, density of the air, velocity, and the area is different, okay? It's the area looking at the plane, and that's going to be drag, and that's what we want to minimize. So I'm going to talk a lot about optimizing the wing. That's what we want to optimize, right? Maximize lift, minimize drag, and we also want to minimize the weight, right? 'Cause the more weight we have, the more lift we need to generate. So we also want to try to minimize the weight. Okay, so right, we know all of these except these coefficients, and what we do is we put the aircraft models into what's called a wind tunnel, and we experimentally measure the two coefficients. Now, in addition to how much area it's seeing, the shape of the aircraft also influences drag. So for each one of these pieces, they all have the same actual area it covers, but they're completely different shapes, and you can see you completely change the amount of drag. So a traditional airfoil would look like this. So our current commercial planes have this, and you can see that does a pretty good job of minimizing the drag relative to other shapes, like a flat shape or a other type of shape. So for the same frontal area, your shape is going to matter a lot too on the drag. Okay. The other component that is also going to influence your drag is called the Mach number. So you hear a lot about in the news or just in general reading about the Mach number. Okay, Mach number is going to be the speed of your object relative to the speed of sound. Okay, so if I have a Mach number of 1, I'm right at the speed of sound. Okay, commercial aircraft tends to be down here in what we call transonic or just under transonic at about 0.7 to 0.85. Okay, so that's the area we're going to be looking at for this project. But clearly we can go higher, okay? What happens is when an object moves through the air, right, you have the air molecules. If it's going low enough, around 250 miles per hour, it doesn't compress, the molecules just move and it goes through. As you start going faster and faster, what happens is the air molecules compress and your density changes, and then you get higher drags, okay? So drag is also dependent on how fast you're going and whether you're having how much compressibility of the air you have. And during the cruise altitude, when you're up, okay, so think velocity squared, that's when your velocity is highest. That's also when you're burning the most fuel. Okay, now how do we get these drag coefficients? You'll put your objects into what's called a wind tunnel. So it's a big tunnel, all right? For instance, I could put this in a wind tunnel. You would put this in the wind tunnel. You have very large fans that are going to generate the air, and then we can sensor up the model, and we can measure all kinds of things. We can measure the pressure on there, the forces on there. You can do visualization techniques of how the airflow is changing around the plane, and that's also how we measure the drag coefficients. You can either put a whole model airplane in it, or for example, this is the new wing we're designing. You can just put one particular component in to look at it too. So wind tunnel testing is a very efficient way of doing a small model and seeing how it performs, and also to measure those drag coefficients. Now, when we're looking at airflow over the wing, okay, there's two types of flow. Okay, one's going to be laminar. So let's think wind tunnel. So if I have my aircraft in a wind tunnel, right, the air is slowly coming over it. Okay, if it's a nice smooth airflow, we call that laminar. Okay. If the air starts being disrupted, we call that unsteady or turbulent. Same thing if you're looking at a river, right? If you have a nice slow-moving stream, the water's all going smoothly, or if you start getting lots of currents and turbulence where it's unsteady flow, that's the same thing, that's turbulent flow, okay? For our aircraft, our new wing we're working on having it be entirely laminar, okay? When it's laminar, it's going to reduce the drag, and it's going to give us more lift. So we're looking for laminar types of flow. So how that looks over an actual wing, right? This is going to be nice, smooth streamlines. So this would be laminar flow, what we want, right? More lift, right? Less drag. And this would be if we look at turbulent flow. So a lot of times you hear about when planes are going really steep, they can have issues, and that's because you get that turbulent flow the higher the angle is at. So we want to avoid turbulent flow, and that's the goal of our new wing, is to have a purely laminar wing. Okay, so the solution to this, to achieve these objectives, is what's called this slotted natural laminar flow wing. Okay, so our current wings have an airfoil shape that's all one piece. All right, this new wing is going to have two. So by adding this extra piece in here and this separation helps us to achieve that laminar flow state. So that's the purpose of this. Also, our current wings that are just one, right, you have all the flaps coming up and down. It takes a lot of hydraulics and equipment. We're not going to have this on this. This is going to be a permanent set wing, so you can eliminate all that equipment, which is going to help us reduce weight. Okay, so we've reduced weight. We're getting laminar flow, so we can reduce drag. Now, the other thing we need to think about is that lift. Okay, so in order to get lift and minimize weight, you typically have very slender wings that tend to be longer to get that lift. Okay. The problem with that is they can become very flexible. So if you think about it, this is really thin and long, right? It can be very flexible. That's problematic, so that's why we put this truss structure piece right here. Okay? Boeing designed this particular wing design. It's called a transonic, which we now know means Mach number 1 a little bit below, truss-braced wing. So this is what the truss brace is, and it's to give that extra support to the wing. So what I'm going to do is actually determine what materials we need to make and what the internal part of the aircraft needs to look like. So I wanted to go over some materials choices we can use. Okay, so one is going to be traditional aluminum. Okay, so I'll pass this around. So this is just an aluminum dog bone. We use this a lot for testing, so we just pull on it and we can get strength and stiffness of the parts. And I brought this back from a lab and TSA detained me, so enjoy looking at this. It cost me a lot to bring it to you. So this is a traditional dog bone specimen, so this is what our traditional metals are like. That's an aluminum. And then what I'm also going to do is pass around this bolt that's titanium. Okay, so you can compare it to the aluminum and see how much lighter it is. So titanium's used a lot. Disadvantage of the titanium, it's very expensive. And sometimes it's hard to get. When I was working on the Joint Strike Fighter, there was a 2-year delay in getting titanium because there were so many large aerospace projects going on at the same time. But you can, if you think about the two, this is just so much lighter than the other one.
Where do we get titanium?
All over. That was another problem, is we were restricted to buying it in America, and that caused trouble too because we couldn't order it overseas. So. Yeah, on the project. So obviously we're going to look at different metals. Another type of material that's used a lot in aircraft is composites. All right, so what composites are is they're made of some sort of reinforcing material. All right, you can either take strands of like for instance, this is e-glass. You can take strands of, say, e-glass or carbon and pull them out straight. Okay, if you look, an individual strand is less than a human hair. So we literally take thousands and thousands of these, and then you put a resin or a matrix on them. Okay, so this is a polymer. It's in liquid form. So what we'll do is it's called laying up the composite. So you'll pick what types of fiber reinforcements you want. Okay, for instance, this one's a woven, a pretty loose weave, or you can have a really tight weave. And then you can also stitch these together. You can do single, and then you lay these up. Okay, you put them in the liquid resin, and then we cook it. It's called curing. And when it cooks, it's going to harden into a composite material. Very stiff. Sometimes you do have some damage tolerance issues on these, but we're getting more towards certification of them.
You got carbon fiber as part of your...
You got carbon fibers, e-glass. There's many, many types of fibers. We're looking at natural fibers. You can do chopped fibers. And we can also add it to manufacture with the polymer and the fiber. So let me pass those around. Another way we can do, and Lockheed's doing a lot out at the Oak Ridge Manufacturing Demonstration Facility, of 3D printing very large pieces. So this is a pretty small one, but this is actually a polymer material with carbon fiber in it, and we can create all kinds of pieces out of that. This was 3D printed, okay, so you can 3D print very complex shapes out of composites. So those are some new emerging materials we're looking at. We can also start joining things. So these are some tests we did at looking at joining metals to composites to take advantage of both of them, all right? And it's really interesting. You can see in this one we bent the piece with the metal on the top. This we bent it with the composite on the top, and you can see they had very, very different failure types, right? This one the composite broke down at the bottom, and in this one they slid apart from each other. All right, but that's what we're going to be doing for this wing, is looking at how can we take the best material for particular parts of the wing and join them together. So joining is going to be a big issue. And this is just fun to look at. We don't necessarily use honeycomb on commercial aircraft that much anymore, but honeycomb is also a very efficient structure. So you take, this actually looks like a beehive. You can do, this one's aluminum foil, this one's titanium, and then you put face sheets on it. Okay, so by spreading the face sheets out, you actually make a much stiffer material at a reduced weight. The problem with these are, and you can see from this one, is you can get core crushing, you can get peel off, and if it's on a plane, it's really hard to detect. So there are even non-destructive methods that they can use to scan it don't always work, particularly if it's peeling off, right? So think about it, if this is under load, even if it's no longer connected, you're not going to be able to detect that during inspection. But we do use these a lot on spacecraft. So they're
What do you use instead of honeycomb design now?
just the metals, the composites, right? Or a lot of times they'll use like a foam core that's not the honeycomb. So that's what we're going to do for the inside structure of the plane. Right. Our research approach, was very evident when you're asking your questions. We're right here. We have a concept, and we need to go back and really work on the details. What new technology do we need? How does all of this work? What analytical tools do we need to improve to be able to design the plane? So we're right here. The next thing we're going to do is start working on integration, so taking all these new tools we made and pull them all together, followed by the demonstration of a wing. And like I said, that's going to take us 5 years, so we're still here. We don't have really have a baseline design yet. We're just conceptually looking at all of this in the first couple of years. TRL refers to technology readiness level, which I'm going to talk to you about on the next slide. So again, technology development, then we'll start integrating it. You're going to see a lot about optimization, okay? And again, that comes to, we want to get minimum weight, maximum lift, and minimum drag. Here are NASA's technology level, readiness levels. So we're pretty much past here. We have a concept. Other companies and Boeing have shown that they work and they have promise. So now it's going to be our job to develop a proof of concept. So taking this concept, deciding, how big does it need to be in between? How are we going to attach the pieces? How long can it be? Where's the best place to put the truss? That's all what we're going to be doing over to take it from a proof of concept to be able to show it in a relative environment, which is a wind tunnel. Right? And then once we get it to there, typically industry takes over and takes it into production. So as far as our education goals, we have a very strong educational component of this too. Like I said, we're going to cover the entire pipeline from kindergarten through graduate school. And all of our activities are based on experiential learning. So learning by experience, providing our next generation with hands-on experience, either directly working on this research or through modules. So what we're going to do for K through 12 and undergraduate education is develop modules that are related to this research. And these will be hands-on activities that different groups can take to elementary schools, high schools, and that all of us can use in our undergraduate classes. For example, I teach Introduction to Aerospace Engineering, so one day we'll do the project and the module as part of our class. We're also going to have internships for the students. Boeing has promised at least one a year to our students. Obviously, working on this project is going to make them more qualified too, so they should have a pretty good chance of getting internships either at NASA or Boeing or any of the aerospace companies, because we do have a lot of undergraduate researchers on this project. For instance, Dr. Coder has 3 and I have 3 just here, plus all the member institutions. Once a year, we're also going to have, it's called a workshop, workforce development symposia. Boeing is going to come and offer training. All the students are going to be invited to come to UT for this one-day workshop where they're going to learn, and then they'll also have the opportunity to present their research and nationwide meet the other students that are working on the project. Focusing on the K-12 outreach, it's really exciting how much we have going on already that we can tie our module into. For example, the Society of Women Engineers has Tomorrow's Engineers Today once a year. It's an entire day where middle school and high school girls can come. They learn all about engineering. It's all activities. They come and actually do hands-on, so they'll be doing our modules. I love this program because their parents come too and do a parallel track, and they learn how to help their students prepare for college and do college applications. So we'll tie into that. Our graduate in our department, we have a really good graduate student group that goes out to elementary schools. So we're going to tie into them. Tau Beta Pi mindset. So Tau Beta Pi is the Engineering Honor Society. We're very fortunate that the national headquarters is in our building. So not only will we be able to tie into the mindset program here, but also nationally. So what mindset is Tau Beta Pi students. So these are our top honor students, go out into the community, elementary schools and high schools, and work with kids. A lot of times it's underprivileged kids to really get them excited about science, and the students like sit and do projects with them, and it's really fun. So we have a very active mindset program here. Tau Beta Pi is also going to put our module on their website, so it'll be distributed nationally through their program, as will NASA. So a lot of these slides we're going to develop more too for the NASA website. Our TL SAMP program also has many week-long programs for 9 to 12th graders, so we're going to tie into that and have our module and have our students and our professors here go to that, and then also Engineers Day, and this is particularly for underrepresented groups. So we're really going to do a lot to tie into outreach, so it's really exciting that all this research will be used for education. And of course, diversity and inclusion. I love the TL SAMP program. I do a lot of work with them. I've gotten some fantastic students from them. I had one young lady who was a sophomore, and she went to a poster competition. She beat out the seniors. She came in second place overall. Yes, I was so proud of her. So I've had just some outstanding TL SAMP students go through my lab. So we work really, Travis Griffin does a lot of work with them. And then also SWE, Society of Women Engineers, National Society of Black Engineers, and the Hispanic Professionals. So we do a lot of recruiting through those groups to make sure we're touching everybody. Also work study, we have a lot of really good work studies here that help. And this is what we're doing at UT, and of course the other schools we're encouraging to do the same level, and I'm gonna work with them to help